Okay, so we're continuing with our study of integrals, and today we're going to be looking at definite integrals. Okay, before we did indefinite integrals, like for example, we tried to find the integral of this, or the antiderivative, and we know that that would be negative cosine x plus c, and we did that last section. Now we're going to look at specific or definite integrals and numeric integration. So we're going to work with numbers more than just functions. So we're building our house of calculus, right? And we have our limits as our foundation, and we did derivatives, and now we're working on that second half, integrals. Okay, there were two very big questions asked in math 400 or so years ago. The first was, how do you find the instantaneous rate of change? And we know that's by a derivative. And now, how do we find the area of irregular regions? And we can answer that with integrals. Okay, so we know basic formulas. We know a circle, we know a square. Maybe you even know this crazy trapezoid-looking shape, okay? Definitely triangles. Maybe not all triangles. Maybe you don't remember how to find a non-right triangle. Okay, but they're boring. They're not exciting. How do you find the shape of something, the area of a shape that looks like this? Okay, how would you find that? And we're going to answer that by integration. All right, so we're going to be talking about summation notation, and let me clear some of that out of there. Okay, so this S is going to tell us the sum of some terms. Okay, we don't know which terms they are. It depends on the function. This symbol is called sigma. Okay, that was like a capital S, so that's why they chose that for the sum. That means add. You're going to be adding. All right, so I down here, that gives our index. That's where we start. Okay, it tells us what number to start at, and N, it tells us where to end. Okay, so we're going to add up certain terms, and we'll see it'll be a little bit better with an example here. All right, so we're going to evaluate this summation. All this is saying is you take your first I, and you plug it in. And then you're going to keep going, adding to the next integer until you get to that upper limit, which was 3. Okay, so this is it. This is the same thing as 1 squared plus 2 squared plus 3 squared. Or if we want to put numeric values on there, okay, would be that, or that would be 14. So this summation is equal to 14. All right, this one looks a little bit more complicated. It's not too bad. Here, our variable is the n. Okay, that's what we're plugging things into. The x is just going to stay there. So if you start this one, we start with 0. X to the 0 plus 1 over 2 to the 0. Okay, x to the 1 plus 1 over 2 to the 1. X to the 2 plus 1 over 2 to the 2. Okay, so this is like our first term, or actually, let me erase that. Okay, this is like our n equals 0, n equals 1, n equals 2. And we're going to continue that. N equals 3, n equals 4, n equals 5. We're going to continue that on until we get 5 there. So we have plus x to the 4th over 2 cubed plus x to the 5th over 2 to the 4th plus x to the 6th over 2 to the 5th this time. Okay, and that's it. That's what this function is. Okay, if you want, you could rewrite this as, whoops, that's a 1, plus x squared over 2 plus x cubed over 4. All right, x to the 4th over 8, x to the 5th over 16, and x to the 6th over 32. That's just a different way of writing this function. All right, so this sigma notation is just a way of summing different things without writing it all out. All right, and we're going to use that idea for area here. Put that up. Okay, we're now going to try to approximate the area of this function. Okay, so to just find the area using our regular shapes, it's not going to be very easy, right? We could have, maybe that looks like a triangle. Maybe there's another triangle, and that's a square, but we're really missing a lot. We're missing this piece, okay? It's not going to work. We're not going to get as an exact an answer if we just use those boring shapes. Okay, so we got to make it a little more exciting, right? And one way we can find the area by summing up different rectangles. Okay, so if I cut this up into, say, 4 pieces, something like this, we could find different rectangles, right? And then add up the areas. So we'll talk about that a little more specific. I want to show you an example here. We're going to use, this was going to be called left hand. Okay, the left hand intervals. Sorry, can't think and write at the same time. So if we want to, let's say we're going to do 4, L4. Okay, we're going to do 4 sub intervals. That's how many rectangles I want to have. So if I want to divide this, okay, the width of my rectangle, I want it to be the same for each one. Sure, it doesn't look like that, but I want it to be the same. All right, so my delta x, whoa, okay, back to that. My delta x equals the change b minus a. This is just in general, or how many intervals I want. 4. So for each of those, this will be my delta x. Okay, and to use this left hand approximation for the area, I would have to draw rectangles, okay, using this left hand value of my function. Okay, that would only be about there, and then this one would be about here. So it's kind of close, right? Maybe some of this makes up for some of the white parts I have. So we could say that the area can be approximated by 4 left-hand rectangles here. And to find the area, that would be equal to the base times the height. So now we got to figure out, what do we call all these x values? All right, I'm going to label those. This can be x sub 0, x sub 1, x sub 2, x sub 3, x sub 4. All right, so this would be f of x sub 0. This would be f of x sub 1, f of x sub 2. It'd be easier if we have a function. It wouldn't be so generic, but that's okay. And we don't need f of x sub 4 yet. All right, so let's say we were going to approximate this area. So it'll be delta x times f of x sub 0 plus delta x times f of x sub 1 plus delta x times f of x sub 2 plus delta x times f of x sub 3. All right, so now we can use this summation notation that I showed you before. Okay, we can approximate the area, okay, by saying it's the sum of f of x sub I times delta x. If we go, that is not an x, is it? All right, there we go. Delta x. If we go from I equals 0 all the way up to I equals 3. Okay, so we can, another way, and this x is going to bother me there. All right, delta x, there we go. So instead of writing out all of these terms, we could write it using this summation notation. Now this would be an approximation using 4 rectangles. Of course, 4 wouldn't be the best number, right? Maybe we could get 8 going on. They'd be different sizes, okay, using the left-hand things, or maybe 16. But the ideal would be to take an infinite amount of rectangles, and that's not something we'll be able to do by hand. All right, but let me write this down. Let me try to go down a little bit. Okay, so let's say as we let delta x get really, really small. okay, then the number of triangles is going to get really big. Okay, that's introducing the idea of a limit. So we take the limit as delta x goes to 0, the sum from I equals 0 all the way up to n, which we're making n would be really big there, of our function, our x sub I, delta x. This would give the actual area, okay, our closest approximation if we had an infinite amount of rectangles. Now, I know this is a lot of weird symbols, and if you have questions, feel free to write them down, okay, but this is going to introduce our new notation that we'll discover pretty soon, okay. This part, sum, right, turns into this interval notation, and kind of looks like an S, so it matches, and it would be the sum of our function, all of the values. This delta x becomes dx. All right, and we went from an x value of a to an x value of b. All right, so this is where we're going with this. We're going to be finding areas under curves using this kind of notation. All right, and now I'm going to just show you some other things. I did a left hand rectangles. I'm going to show you right hand. So this time you come up from the right hand side and use that function point. All right, so about here and here. All right, so that would look different. The area would be a little bit different, and this would be a right hand approximation. All right, another method, another way I could do it, I could draw my triangles by using the midpoint. All right, so let's see. So it looks like maybe this would be the midpoint of those two x values. Okay, and that would be the midpoint. And that would be the midpoint here and maybe about here. Right, and this looks like it's getting a little bit closer to the actual area. So that was our midpoint method. And then another method would be a trapezoid. So most people think of trapezoids like this. Okay, but this is also a trapezoid with like a right angle there. And we could turn it around, and a trapezoid could look like this. And of course, you remember the area, 1/2 the sum of the bases times the height. And we'll be using that later. Okay, and then we could approximate area using trapezoids. So then this, instead of drawing a curved line, we draw this straight line. Okay, from here to here, here to here, here to here. Okay, and so now we're even closer. We're able to get a little bit closer to maybe what that actual area is. All right, so the next example, I want to start now. I want you to try a couple, and then maybe we can finish this in class. This is a really big idea. All right, so we're going to use 4 subintervals of equal width to approximate an area under a specific curve. All right, so if we were going to find the area, to find our delta x, we have 4 subintervals. So our change in x, our delta x, is equal to 1, the b minus a, okay, our actual endpoints that we're talking about, divided by the number that we want to use. So it'll be 1/4 in our case. All right, so we're going to split it up into 1/4, 1/2, 3/4, and we have this 1. Okay, and then we're going to draw these triangles to help approximate our area. So the area can be approximated. Anytime you use approximate, you want to put a squiggle, all right? L4, so we're going to use 4 left-handed rectangles, sorry. All right, so they're going to look something like this. All right, and by how, since we have the picture, it's really helpful. You're going to see this is going to be an under approximation. It's not going to quite get to the exact value of the area, but it's going to be a good approximation. So let's see, if we're going to approximate, that would be 1/4 times f of 0. Okay, if we want the height, that's f of 0. This will be f of 1/4. Okay, this will be f of 1/2. This will be f of 3/4. Okay, that's where I'm coming from. I'm just writing down the areas. 1/4 times f of 1/4 plus 1/4 times f of 1/2 plus 1/4 times f of 3/4. Okay, this is just writing out the area. When you're doing a free response problem, you really want to show them what you're thinking. Okay, and this is a great way of doing that. 1/4, there's 1/4 in all of these. Since we have equal widths in our rectangles, okay, we could also write it as f of 0, f of 0 plus 1/4 plus f of 1/2 plus f of 3/4. All right, now we just have to go back, find the values, and get a number. So 1/4 times, this will be 0 plus, what's that, 1/16, 1/4, 9/16. All right, and if we want to change that, that would be 4/16, right? So we'd end up with 1/4 plus 14/16. All right, or 1/4 times half of that, 7/8. So our approximation would be 7/32. All right, and that is an under approximation, remember, because if you draw the rectangles, they're underneath of the curve. So in your whisk, and what I'd like you to do tonight, it shouldn't be too tough. What I want you to try now is to use the right hand. Okay, so you're going to find area. It's going to be approximated by 4 right hand subintervals. So you're going to use similar numbers, okay, but your endpoints are going to be on the right for your triangles. So now you're going to have this over approximation. So you're going to use similar numbers, okay? You're using the 1/4, 1/2, 3/4, and 1. But then you're going to use f of 1, f of 3/4, okay? F of 1/2, and f of 1/4. That's something that, like I said, I'd like you to put in your whisk. You're not going to use that f of 0, though, because you only have this, all right? So compute the actual area, just leave it as a fraction, and put that in your whisk. Have a great